followed by.
Okay. So on behalf of Tamil Nadu Science Forum and Popular Science Lecture Group, I extend my warm welcome to you all. Today we are going to have a webinar on dark matter and its detection by Dr. Surjeet Rajendran, Associate Professor of Physics, Johns Hopkins University, Maryland, USA. We have with us two pillars of PSL, Dr. TRG and Dr. Ramanujam. We see the registration not only from Tamil Nadu, but from other parts of India as well as from other countries. Hence, this meeting shall be in English. We should like to have a brief introduction to Tamil Nadu Science Forum and the speaker. This is the program schedule of this webinar. First, Dr. Ramanujam shall introduce TNSF, followed by the introduction of the speaker, Dr. Surjeet Rajendran by TRG, Dr. TRG. Dr. Surjeet Rajendran shall speak for 45 to 60 minutes and we'll have a question answer session about 30 to 45 minutes. Vote of thanks shall be by Pugadarasu, our EC member who has just completed his bachelor degree in physics and going to pursue his higher studies in Bonn University, Germany. We will try to wind up this event by 8 p.m. PSL is part of TNSF and started functioning in 2018 only, although the TNSF is functioning from 1980 onwards. PSL came into existence when we decided to strengthen the activities of TNSF in the higher science area. We have conducted 38 lectures so far, and this is the 39th lecture. The first lecture was held in 2018 as Stephen Hawking's Memorial Lecture. PSL used to have its lectures in the hall and it adopted virtual meetings during the pandemic period. We hope we may have few more virtual meetings till the pandemic is over. I request all of you to mute your mic and video. As the lecture progresses and any question arises from any of the participants, please post it in the chat window. Your question will be read and answered during the question answer session. During the question answer session, if any of you want to chat directly with the speaker, please raise your hand and we will allow one by one to speak simultaneously. The questions from the chat window shall also be addressed. We would like to get feedback from of this webinar from you, and we posted a Google form. The link for this is provided in the chat window. Please fill up the form provided by you by providing your contact details and your opinion of this program. We will keep your contact details confidential, and that shall be used for communicating our future programs only. In the meantime, I request you to provide your email ID in the chat window by choosing me in private chat. We also have Telegram group meant for PSL. To join the group, click the link provided in the chat window. You will get the notification of our programs in mobile through the Telegram. With this, let me hand over the mic to Dr. Ramanujam to introduce the Tamil Nadu Science Forum. Dr. Ramanujam, please.
நண்பர்களே அனைவருக்கும் வணக்கம். முதல்ல தமிழ்நாடு அறிவியல் இயக்கம் பற்றி ஒரு சில வார்த்தைகள் தமிழில் கொஞ்சம் சொல்லிட்டு and then I will speak in English as well. முதல்ல தமிழ்நாடு அறிவியல் இயக்கம் ஏற்கனவே சொன்னது போல 1980 துவங்கியது. சென்னை பல்கலைக்கழகத்தில் இருந்த சில ஆராய்ச்சி மாணவர்கள், இங்கே ஒருத்தர் உட்கார்ந்திருக்காரு, ப்ரொஃபஸர் கோவிந்தராஜன், அவர்கள் ஆரம்பித்த ஒன்று. அறிவியலை மக்கள் மத்தியில் எடுத்துச் செல்வதற்காக பல வருடங்களாக, குறிப்பாக அறிவியல் கல்வியை பொறுத்த வரைக்கும் மாணவர்களுக்கு வாழ்க்கையொட்டிய கல்வி, அன்றாட வாழ்க்கையில் அறிவியல் கல்வி, இவற்றையெல்லாம் மாணவர் மத்தியில் எடுத்துச் செல்வதற்காக இந்த அறிவியல் இயக்கம் அரிய பல பணிகளை செய்து வருகிறது. பொதுமக்கள் மத்தியில் அறிவியல் பரப்புதல், அது மட்டுமல்லாமல் கல்வியில, துவக்க கல்வியில, பள்ளி கல்வியில பலவிதமான தலையீடுகள், அதோடு சேர்ந்து சுகாதாரம், மக்களின் சுகாதாரம் மக்கள் கையில் என்ற அடிப்படையில பலவிதமான செயல்பாடுகள், அதோடு சேர்ந்து அறிவியல் பதிப்புகள், பல வகையான அறிவியல் பதிப்புகள் குழந்தைகளுக்காக, பெரியவர்களுக்காக என்று, அது மட்டுமல்லாமல் ஆண் பெண் சமத்துவத்தை வலியுறுத்தக்கூடிய முக்கியமான பல செயல்பாடுகள். இது போல அறிவியல் இயக்கம் பல அரங்கங்கள்ல அறிவியலை எடுத்து செல்வதற்காக அறிவியலுக்கான ஒரு மேடையாக விளங்கி வருகிறது. அதோடைய ஒரு அங்கமாக இந்த மக்கள் மத்தியில இன்றைய அறிவியல் ஆராய்ச்சி எவ்வாறு செல்கிறது என்று மக்கள் புரிந்து கொள்வதற்காக இந்த குறிப்பிட்ட வரிசை பல உரைகள் நடைபெற்றுக் கொண்டிருக்கின்றன. அதில் பல விஞ்ஞானிகள், அறிவியலாளர்கள், இன்றைய அறிவியல் ஆராய்ச்சி, கட்டிங் எட்ஜ் ரிசர்ச்னு சொல்கிறோம், அப்படின்னா அதை எவ்வாறு நாம் புரிந்து கொள்வது என்று மக்கள் மத்தியில் எடுத்து செல்வதற்காக, குறிப்பாக கல்லூரி மாணவர்கள் மத்தியில் இதை எடுத்து செல்வதற்காக இந்த உரைகள் நடைபெற்றுக் கொண்டிருக்கின்றன. வந்திருக்கும் அனைவரையும் அதற்கு வரவேற்கிறோம். Friends, it's a pleasure for me to mention a little bit about Tamil Nadu Science Forum before we get on. Tamil Nadu Science Forum was started by a group of research scholars of Madras University, and in the last 4 decades has been involved in science communication and science popularization at various levels. One important aspect of Tamil Nadu Science Forum's work has been in science education, especially in schools, restoring the primacy of experiments, science experiments, relating science to everyday life, and getting teachers and children to understand about hands-on science. Another aspect has been science popularization among the general public, with a variety of publications, slideshows that have been taken up at various levels, science exhibitions, and these have been going on for many years. One more aspect of Tamil Nadu Science Forum's work has been in the area of health, especially in the area of reproductive health in rural areas. And another dimension is looking at gender issues, gender equality, and in the context of science communication. So a lot of science and society issues have been taken up, and among these, this particular series of lectures has a pride of place as talking about what happens in scientific research, inviting scientists to share experiences of their research with the general public, especially with college students. And this has been a remarkable journey for us, and we are very happy to invite you and join this journey and take it further. Thank you very much. Over to Professor Govindarajan to introduce the speaker.
Okay. Thank you, Jam Ramanujam, for this nice introduction about TNSF and PSL. Now, it's my pleasant duty to introduce the speaker, Professor Surjeet Rajendran of Johns Hopkins University. Now, he's actually a good friend. For the past few years, I've been in touch with him on issues of dark matter, which is one of the titles for this thing. And it is very interesting to hear from him. And the background of him is also very interesting. In fact, his family I knew very well. They are very good friends. And I can also tell his grandfather attended my marriage, which was held in one of the halls. And of course, in registered marriage. So he was also present. Few people who were present, he was also there, very interestingly. But now Rajendran, his father, was well known to me also at that time. And Surjit, I've been hearing about him earlier. Now I'm also being in touch with him by email. Now Surjit, he did his schooling in Chennai, Padma Seshadri School. And as usual, many of these students from these schools go to some very good places like IITs and natural route. And he went to IIT Bombay. If I'm correct, he did engineering physics. Is that right? That's right. Engineering physics BTech. And then from there, of course, I knew several professors from IIT Bombay who must have taught him, like Shenker, Urjit, etc. And my student is also there right now as a professor in the Department of Physics. A couple of people I know, I'm even collaborating with them. Then he moved to Caltech, where he did his mathematics. Very interesting. He went from engineering physics to mathematics. And after getting a degree in maths, he also started doing PhD in physics, back to physics. Under Dimapoulos, Savas Dimapoulos, right? Your advisor was Savas Dimapoulos.
Yes, that's right.
Who's also, I met him in ICTP and other places. And very interesting. In fact, I keep meeting some of the names which he has been associated with. So he did fantastic work for his PhD. and he won. Well, this is a story. He won some great awards, and I'm going to mention two of them. One is this New Horizons in Physics by famous Milner Foundation, Milner Group, who gave about 2017 a huge prize. He shared, the prize was shared with two more people, if I'm right, and who were in Perimeter Institute at that time. And for his work on developing inventing new methods of discovering dark matter, dark energy, and gravitational waves. And his work is very well recognized in the world of physics, because I do follow it, this thing, and there are several laboratories who are also trying to use his work to find out. And then after his Stanford, he went to for postdoc at MIT, if I'm right, and then back to Berkeley as a Shenker physics professor, Henry Shenker professor in Berkeley. And recently he has moved to Johns Hopkins University. He's there for the past 1 or 2 years.
2 years now. Yeah.
2 years now. And he has also won another grant, a huge grant, Simons Foundation, which gives a huge grant. And that with that, he can do any amount of research, hopefully very well. And also involve many students, postdocs, and also other researchers. And I'm sure his visit to India will be very fruitful. If I hear he comes very regularly, but he has never visited my institute once. Now I'm going to force him to do that. Every time he comes to Chennai, he will visit. And I'm looking forward to his talk. This is about dark matter and its detection. I'll just briefly mention about what is dark matter, because many of the people may not know. So we know Newton's theory of gravity, okay, where solar system issues about Kepler's laws, etc., were explained very well. But there were some problems with that, like precession of Mercury and other issues. But as far as possible, Newton's law of gravity worked very well for 400 years. No problem with that. Then came general theory of relativity given by Albert Einstein, and which took filled the gaps which were there with reference to issues about the precession of Mercury. But also, new important thing is even light is attracted due to gravity. Even light is pulled by gravity, which was a major thing by Einstein's work. And people were very happy with nearly 20 to 30 years after that. But then it led to a lot of developments, led to the ideas, understanding of the whole galaxy, even universe, various things developed. And we find now a new situation, which is, for example, if you take solar system, planets far away move very slowly, and planets close by move very fast. That is one of the Kepler's laws. And we expect similar thing for the galaxies. And the stars far away should go very slowly, and stars very close to the center of the galaxy should go very fast. But it doesn't happen. So it raises the question, should we revise Einstein's theory of gravity? Or is there some other matter which we don't know? Like, for example, we are all made up of protons and neutrons, and we are all made up of various atoms, elements which are there, molecules. And also solar system, sun is made up of hydrogen, helium, etc. And should we have a new particle maybe one or two or many of them, which are filling up the whole universe or whole galaxies, which is making this change which is there. So it is asking very, very fundamental question about our galaxies, how they are formed, what is the role, etc., beyond the solar system, which we have been knowing quite very well using Newton's and Einstein's theory. So this is the status, and dark matter and dark energy plays a very important role in the origin of the universe, the evolution of the universe, how the galaxies were formed, and all those things. And the scale of physics takes from solar system of few light years to millions of light years. And we are going to talk about such a extraordinary development which has taken place in the last 60 to 70 years, if I'm right, maybe think, and which many of the students and think may not be aware of these changes. And I'm hoping Rajendran, Surjeet will explain many of these things and create a lot of interest in people who are attending, so that they take up further, students particularly take up further work and also find what is dark matter. Now I will stop, and one more information for completion I will give you. He went to US, he was supposed to go to US on the day when it was bombed by the Al-Qaeda on September 11th, I've heard. But it turned out because of his flight was cancelled, and then he had to leave after 2 to 3 weeks. So this is also a nice tidbit to hear, but things are different now. Okay, now thank you, Surjeet. Now it's up to you.
Yes, thank you very much for this very nice introduction. It is true that I have never visited TRG's institute, but actually I've gone there when I was a student, when I was in high school, but I didn't go TRG back then. So yeah, so this is a bit of a challenging talk for me to give, because the audience ranges from my father to college students who generally know more physics. So I've tried to pitch it somehow in the middle of these two sorts of differences. So in case, I mean, there will be content in my slide, but I will not necessarily focus on what's on there. I will try to make this as informal as possible so that people feel comfortable asking questions should you need more explanation on any topic that I'm talking about. So the way this talk is going to work is that in the beginning, I will just give an overview of dark matter. This will basically be what TRG just talked about, but I'll show some more pictures so that it's more comfortable for people. And then I will talk a little bit about traditional work in the area. And then I'll sort of briefly touch on what I have been up to for the last few years. So that's kind of the overall plot of the story. Okay. Right. So a basic question that we might want to know is, we know that we live in a galaxy, and we want to know what is in the galaxy, right? What do we have? And the simplest way of understanding what is in the galaxy is to take a telescope and look into a telescope and see what's in the galaxy. And we can ask, what do we see? Right. So it's a simple enough story. Just take a telescope and look at what's there. What we do see when we look into a telescope at night and look into the galaxy is that we see stars. Those are the luminous things that we're actually seeing. And the second thing we see is gas. Basically, the stars are lumped objects, right? A star is a lot of mass, a lot of matter in one object. So, and it's luminous, it's glowing, that's why we see it. And then there is just individual molecules of gas that are spread all over the galaxy. Okay. So it turns out that if you ask what is the amount of matter in the gas and what is the amount of matter in stars, it turns out that about 99% of the matter that we typically see is actually in the gas, and only about a few percent is actually in stars. So this is a little surprising, because you might think naively that given what we typically see with our eyes is the stars, you might think that most of the matter should actually be in stars, but that's not true. The gas is not very dense, but it's distributed over a very, very large region. So even though the density of the gas is small, it's spread over such a large volume that the overall mass in the gas is much larger than the mass in the stars. So that's just what we can see. Okay. This raises a very interesting question, though, which is there anything else in the galaxy that we are not actually able to see? Do those things exist? And the question becomes, if there is something that we cannot see with our eyes, how can we find out if there is something out there that we cannot see, right? How, if it doesn't emit light, if it does not glow, how can we know it's there? What we can do is we can make use of Newton's theory of gravity. Newton famously discovered in the 1600s that every object in the universe has a gravitational force around it. It attracts every other body in the universe with gravity. So for example, Newton recognized that the reason why apples fall down to the ground is because the earth, through the force of gravity, attracts the apple. And the apple also attracts the earth through the force of gravity. Similarly, the sun attracts the earth through the force of gravity, and that's why things are moving around. So gravity is a universal force. No matter what the nature of the object, whether it glows or does not glow, whether it has light or is dark, whatever it is, gravity will act on it. So the thing you can do is that you can make use of the universal nature of gravitation to try and see if there are other objects in the universe that are not emitting light, but at the same time have to react or create gravity, because gravity does not care whether these things are emitting light or not. So here is the main idea for dark matter detection, or sorry, not dark matter detection. The way we realize that dark matter existed is that even if we somehow cannot see an object, we can see the gravitational effects of that object on other things. So for example, in the 1800s and things like that, we discovered planets, okay, such as Uranus, based upon their effects on Saturn. So we did not know that Uranus existed because we couldn't see it in the telescope, with the telescopes people had back in the day. But what people actually were able to do was that they were looking at Saturn. That's the planet we were able to see very nicely. And they noticed that Saturn was not moving the way you expected it to move. So in the sense, if you thought Saturn was moving solely due to its the gravitational force of the sun, Saturn would have moved in a certain way. But once in a while, we found Saturn was doing something strange. And that led people to realize, well, maybe there's a planet out there, okay, which we're not able to see, but the gravitational effects of that planet is clearly being visible on Saturn. And therefore, by observing Saturn, we were able to infer the existence of Uranus. That's kind of how people knew that we should go and look for Uranus, and they discovered Uranus. So you can ask the same kind of question. What can I see in the galaxy which will allow me to learn if there are other constituents in the galaxy, if there are other particles, if there are other objects in the galaxy that we are not able to see, but are nevertheless exerting a force of gravity? So we want something like Saturn that we're able to see in the galaxy and use the motion of those objects to figure out if there is some other matter in the galaxy. And of course, the natural analogy of Saturn and the galaxy would be other stars. So the stars we're able to see very easily in the galaxy. And so we can look at how the stars are moving and see if the motion of the stars is what we expect it to be. And if it is not what we expect it to be, we can use that fact to say, oh, there's something else out there that we cannot see, right? So that's kind of the idea. So this was exactly the program by this guy Zwicky, okay, in the 1930s. What he did was he launched a program to go and observe the speeds of various stars in the galaxy. So he had a telescope and went around looking for the speeds of various stars in galaxies, okay? So he looks at a particular star, he knows how far away that star is from the center of the galaxy or something, and he's basically saying, okay, how fast are these stars moving? So he's just going and making measurements. And then I will put a little bit of mathematics in here, but if you're not familiar with the mathematics, you can follow the words. But essentially, the idea is that if you look at the velocity, the speed of these stars, you can ask if the speed of the stars is obeying the law of nature, which is Newton's law of gravity. So Newton would basically say that if I have a star and the star is going with a certain velocity, with a certain speed, and I'm assuming that the star is moving with that speed because of the gravitational force of the other stars or gas that it's exerted, that's around it, Newton's law, Newton's equations tell you what that speed should be. That is this mathematical equation, gm over r squared is equal to v squared over r. But it's just telling you that this speed, the velocity that Zwicky is measuring, is tied to the overall amount of mass, which is this quantity m. Okay, there's an equation that relates these two things. So you can go and do that measurement, and you can basically ask if the speeds that you observationally measure in the sky are what you would expect from Newton's law or not. So as TRG mentioned earlier, the analogy you want to have in your head is the following. If you look at planets in the solar system, planets in the solar system are dominantly moving due to the gravity of the sun. The sun is the largest mass that is in the solar system. And what we see is that the force, the gravitational force due to the sun drops as you go further and further from the sun. So Mercury has a much larger, the gravity of the sun on Mercury is much bigger than the gravity of the sun on, say, Pluto. And because the force of gravity that's on Mercury is much bigger than the force of gravity on Pluto, Mercury goes around the sun more rapidly than Pluto goes around the sun. Okay, so the naive expectation that we will have going in is that if I see these stars, okay, just like in the solar system, the further away you go from the center of the solar system, the speeds of the planets keep decreasing. Similarly, you would expect that in the galaxy as well, the further you go from the center of the galaxy, the speeds of these stars that are going around the center of the galaxy should keep decreasing. That is what you would naively expect. So this is a plot. Okay, I don't know when the plot was made, but this is sort of the rough idea of what you're seeing. So this is in the x-axis here. This is the distance that we have from the center of the galaxy. And on the y-axis here is the velocity of stars that are actually observed. All right. What you might expect, if you think that the galaxy is a lot like the solar system, you would expect that as you go away from the center of the galaxy, the speeds of all these stars should drop as you go further out. So I hope you can see my cursor. So it basically would show that the further away you go from the center of the galaxy, the speeds would keep dropping, right? That's what you expect naively from theory. But what we actually see is not this theoretical prediction. What we actually see is that the velocities go up a little bit and they kind of more or less remain constant. So there is a pretty significant discrepancy between what was observationally measured by Zwicky and many other people afterwards, specifically this person by the name Vera Rubin, versus what was actually theoretically expected. Okay, so this is very straightforward evidence, observational evidence, that there is something that is going on there that we are not actually able to understand, because this is a deviation from Newton's prediction, much like how when we see Saturn is not moving just like how Newton predicts, right? That's because when you're making a prediction, you didn't include Uranus. So that's why your observations of Saturn are different from what Newton's theory would naively tell you until you realize that you had to include Uranus also in the picture. So this is a very similar kind of analogy that's going on right now. But this is the sort of thing that you should ask a question about. Yes, there is in fact a observational discrepancy between the prediction of Newton and the actual observational facts, right? So this, the fact that these two lines are not on top of each other is telling you Newton's theory of theoretical prediction is not what we're observationally seeing. So it raises a natural question. Is there some other mass that is in the galaxy that we are not able to see, but it's acting gravitationally? So we would call that dark matter. Okay, so one interpretation of this data is that we are saying there is some other matter in the galaxy that we are not able to see. That's called dark matter. And a number of us want to go study it. But you should ask the question, well, how do you know that dark matter is the only possibility? After all, Newton's law itself could be wrong, right? Why does Newton get the authority to make a law that is true forever? Is it not possible that Newton, a human being just like you and me, he came up with a law, he was trying to explain some observations. Perhaps Newton's law is just also wrong. Something, is wrong about it. So that is an interesting question. Okay, this is again not my work. I'm just reviewing what is known. And what we observationally know is that the observed speeds, which is the right-hand side of this equation, the observed speeds do not match the observed masses in the galaxy, right? So we know that this equation does not hold. The idea of dark matter is that there is more matter out there than we can see. But that's one possibility. And the other possibility is perhaps, well, maybe this law was fundamentally wrong. Newton just got it wrong. So one can ask this question, well, how easy is it to change Newton's law of gravitation? I mean, one can easily say those words. It turns out that making that a reality in terms of writing down a theory that makes sense, etc., is considerably harder. Okay, gravity is famously a force that is hard to change. But we can ignore that. We can just be like, look, maybe you theoretical physicists just aren't that good, right? Maybe it is the case that someone who will figure out one day in the future how to change gravity in some sensible way. You can ask this question observationally. Observationally, how can I tell the difference between Newton's law being wrong and there being extra matter without having to make arguments about theories? What can we do? Okay, so to do that, we would really require some system where the dark matter and the visible matter are well separated, right? Because we are trying to distinguish the fact that Newton's theory of gravity is wrong from the existence of extra matter. Now, Newton's theory being wrong basically suggests that, look, there is only the matter that we see. There is no extra matter, but somehow the force of gravity from that matter is incorrectly being calculated by Newton's equations. So what we want to know is basically if there is a system in the universe where we know for a fact that the visible matter is in some place, but whatever dark matter, if it's there, okay, we're testing for the existence of dark matter. Suppose dark matter and visible matter, they're not mixed together. So in our galaxy, the problem is that the dark matter and the matter are in the same area, right? The dark matter and the matter are in the same galaxy. And so we are not able to distinguish whether the effects we are seeing on the stars is because of a change to gravity or because of a new particle. So if somehow there was a system where the visible matter and the dark matter were separated, then you could ask, is the force of gravity working like you think it should, or is there a new particle? So I will explain this more in the coming slides. So it turns out what we need to look at are objects called merging clusters, and I'll just tell you what merging clusters are in the next slide. So what is a cluster? Okay, a cluster is nothing but a large number of galaxies. So we know that the solar system is one star with 9 planets, and if you take like a trillion or so stars together, they're going around each other, that forms a galaxy. Now, it turns out the galaxies are not the largest objects you can think of in the universe. What happens is basically there are on the order of 1,000 galaxies or so that are going around each other. Okay, so we are part of something called the Virgo cluster of galaxies. So there's a large number of galaxies that go around each other, and those get the name of a galaxy cluster. Okay, so these are in some sense the largest gravitational structures in the universe. So all of these thousands of galaxies going around each other that really does exist in the universe. So when you have all these clusters, it turns out that in the aeons of time, in the billions of years that the universe has existed, once in a while, one of these clusters will merge with another cluster. So what we are showing in this picture is that we have one cluster of galaxies, and there's another cluster of galaxies, and they are getting gravitationally attracted to each other. So they come towards each other, and as they come towards each other, they'll start hitting each other and merge. Okay, so it's a little bit like you can think of it like an asteroid or something coming and hitting the Earth, right? Like gravitationally, there are these things going around, and once in a while they just go and smack into each other. So we do see this in the sky. We certainly see the one cluster of galaxies occasionally merging with another cluster of galaxies. And then we can ask, when such a merger happens, what's actually going on? Okay, so here's a picture for that. So let's say this is one cluster of galaxies and this is another cluster of galaxies. What we have in these galaxies is basically some number of stars. Those are the stars that are visibly drawn over there. Okay, and then there is the gas. And the key point is that the stars are, even though they have a bunch of mass in them, they're small, right? A star is, the sun is about 500,000 kilometers in size. It is very tiny compared to the overall size of the galaxy. All right, the size of the galaxy is enormous compared to the size of a star. So the stars occupy a very, very small part of the volume of the galaxy, while the gas is distributed all over the galaxy. Okay, so what's happening is that as these two galaxy clusters, for example, merge, the gas, which is all over the place, everywhere, okay, all these green dots, they will easily run into the other green dots in the other cluster. So basically, this is one cluster, this is another cluster. These are the small number of stars in each cluster, and this is the large amount of gas in each cluster. And as these guys are merging, the gas on this cluster will go and easily find another gas particle here and hit it. While these stars, since they occupy such a small volume of the overall size of the galaxy, it is extremely unlikely for one star here to go and hit another star in the other cluster because of the fact these guys have such a small volume of the overall galaxy. So what happens is that these gas particles, as they go through each other, so this gas particle from here starts merging, this gas particle comes from here, they'll hit each other. Okay, so you have a little bit of gas coming from this side, a little bit of gas coming from this side, and they smack into each other. As they smack into each other, with quite a lot of velocity, it turns out. And when they collide, they are going to get very hot. And it starts glowing. Oh, sorry. I don't know why my email showed up there. One second. I don't know what happened there. All of a sudden. Let me stop the share and start it again. So that. Another interruption. Okay. All right, sorry about that. One always has to have some technical difficulties in a theoretical physics talk, otherwise it wouldn't actually be nice. All right.
Yes.
It's back again, right? Yeah.
Yeah.
Okay, good. All right. So indeed, so as this thing goes together, these two things will start colliding and the gas will get very, very hot. That's the basic idea that we actually have. So this is what we expect, right? The colliding gas will get very hot while the stars will go right through each other. Now, here is the main point about dark matter. So our idea about dark matter is that we basically have one cluster where I have a bunch of gas particles sitting in there. Those are the green things. The stars are, of course, the stars. The black dots are the dark matter particles themselves. So we're assuming there is dark matter, right? We want to test for dark matter. And we want to say, okay, suppose this galaxy cluster has a bunch of dark matter, which we're not able to see, but its gravitational effects they're able to see. And we have another cluster that also has a bunch of dark matter, okay? So what we would expect is that as these galaxy clusters are merging, if the dark matter itself does not interact with itself or the gas, right? So we're assuming the dark matter doesn't do much scattering. It just goes right through. If that is the case, we would expect the dark matter would go right through each other without colliding. And it will basically track the location of the stars. So the stars don't hit each other. So the stars go right through as this collision happens. The dark matter also, we expect, if it doesn't interact very much, it will also go right through. While the gas, which is the most of the mass in the galaxy, the gas collides. And as the gas collides, it will get stuck in the middle and get very hot. So our naive expectation should be that the dark matter should be the same location as where the stars are, while the gas in the system would be in a different location and it would be very hot. So this is the most famous of these pictures. It's called the picture of the bullet cluster. And that is essentially a picture of these two galaxy clusters merging. So what has happened is that we're, of course, seeing this picture after the event has occurred, right? So there were two galaxies clusters and they merged, they went through each other. And what we see is the fact that in this particular system, there is this red region here, which is extremely hot. We see this in X-rays, it's extremely hot. And that is the hot gas as a result of this merging cluster, which collided and got very hot. And then we have these locations on either side of this picture, which are the locations of the stars that used to be in these galaxies, but then they got stripped. They kind of went through each other like that, right? So this is a perfect example of a system where the gas is separated from the location of the stars. And now comes the question, which is where is the dark matter, right? Like, can I use this system somehow to distinguish between the possibility of the existence of dark matter, which is my naive assumption, versus a change to Newton's law of gravity? So here is a fact about the world. We know that the visible matter, thankfully, right, is mostly gas. 99% of the galaxy's mass is actually in the gas as opposed to in stars. So what we would expect is that if our observations in the galaxy about these speeds not working properly, if those are actually somehow due to a change to Newton's theory of gravity, if that is the case, then we would expect that the modified gravity would track the location of the gas, right? Because the gas here contains most of the mass of the galaxy. And if the observations of dark matter were due to a change to the law of gravity, we would actually expect that most of the gravity should track the location of the gas because the gas is, in fact, most of the mass. While if it's the other possibility, if it's actually due to dark matter itself, if dark matter was the source of these discrepancies, we would expect that the gravity of the system would actually track the location of the dark matter, which is on this side. And the dark matter, very nicely, we expect it to be where the stars are, right? So that is the key question. The key question is, in this merged cluster, is most of the gravity of the system in the location of the gas, which is most of the visible mass, or is it in the location of the stars, which is where you would expect most of the dark matter to be? So that's an observational question that one can go and answer. So this raises a very interesting question, which is, how do we measure the gravity of the system, right? How do I know where the gravity of the system actually exists? And to do that, we use one of Einstein's most famous predictions, which is a prediction of what is called gravitational lensing. And that's a very intuitive idea. We are used to the fact that if you have a gravitating body, and I, let's say, throw an object at this gravitating body, like a rocket or an apple or whatever it is, the gravitating body, like the Earth. So if I take the Earth and I throw an apple at the Earth, I know that the apple will bend and fall towards the Earth. We are used to this all the time. Einstein predicted that this bending should also happen for light, right? So basically, if you had light falling towards a gravitating body like the Earth or the Sun, or really anything that has any kind of mass, Einstein predicted that the light will also bend because of this gravitating, or because of gravity, essentially. So you can do what is called a gravitational lens, which is the following idea. So imagine I'm sitting on a satellite somewhere and I am observing some very distant object like the star or a galaxy or something like this. And suppose this galaxy in the middle did not exist, okay? So the galaxy in the middle did not exist. What would happen is that the light from this galaxy would come straight to us without bending because it's just going through empty space. But what's happening now is the fact that because I have this galaxy in the middle between this star and this observational platform, this telescope, the light that is being sent out by this galaxy is going in all directions. So as this light goes in various directions, because of this galaxy here, this light will start bending. Okay, so instead of it going straight, it starts bending. So this light that normally, if I look at where this light would have gone, right, this star or galaxy emits some light, that light, let's say, goes in this direction, it wouldn't have normally come to you. It would have normally kept going straight. But what's happening is that as this light goes out here, because of this gravitating object here, the light starts bending. And as it bends, it comes towards the satellite, right? So this has a very important consequence, which is that if I look at this particular star or galaxy here, I will actually see, in some sense, multiple images of it, because what's happening is that the light goes from here, it starts bending and comes over here. And if I'm standing here, I will basically see the star as coming from somewhere at this location. I'll track it back here if I go follow this line. Similarly, if I look at this particular light ray, it comes over here. Here is this star, this galaxy. It starts bending. It goes over here. And once again, if I look over here, I'll basically see that, oh my God, this particular galaxy is appearing to come from here and here. These are two images of the same galaxy. Okay, so that's called a gravitational lens. Now, the important thing about the gravitational lens is that I can actually observe these images and use that as a way to infer the amount of mass between this galaxy and me, right? I can just measure the amount by which this light is bending and use that bending of the light as a way to figure out how much mass there is between me and this galaxy. So that is a very interesting program to do, where we use these observations to figure out what's between us. So this is something we can actually do with this bullet cluster, where once again, to remind you of the story, in the bullet cluster, what's happening is that two clusters merge together. The hot gas is in the region in the middle. The stars are on either side, and the dark matter we expect should also be on either side. In Newton's theory, or if it's a modification of gravity, we would expect that the gravity of the system is in this region in the middle, which is where most of the hot gas or most of the matter, actually the visible matter, is. While in the dark matter situation, we expect most of the gravity to be on this side, at the location of the stars themselves. So what we actually have seen with these lensing measurements, so the lensing measurements basically work by trying to look at objects behind this stuff, right, behind this merging cluster. So we look at some star somewhere here and somewhere here on either side of these things. And we ask, well, where are these stars maximally bending? Where is the light from that star maximally bending? It turns out that most of the bending actually happens at the location of the dark matter, as opposed to the location of the stars. So that is conclusive evidence, okay, of the existence of dark matter as a new particle, as opposed to a modification of gravity. Because if it is a modification of gravity, most of the effects will actually be on this side as opposed to over here. So this is basically concludes the first part of my talk, which is overall telling you why there is a particle to call dark matter, what is the observational evidence for it, and why do we think it's a new particle as opposed to a change to the law of gravity. So I'm happy to pause here for a second to see if people have any questions. If there aren't any questions, I can move on to the next part of my talk, where I will talk about, briefly highlight what are experimental ways in which we can actually detect dark matter and try to understand its properties. So let me take a second to pause and see if there are any questions.
So
yes.
What if, okay, so from this you can say that there is dark matter, but you might still need to change the equations of gravity, right? Because it's about finer calculations and you may need to do that, right? Or is it already enough evidence to see that you don't need to?
Well, so I mean, it is certainly possible that there could be a modification to gravity. I mean, I think that's an interesting question. It's more like we can say that what this shows is that the dominant effect, right, that is not due to a change to gravity, but rather due to a new particle.
Yeah. Thanks.
Sure. I think there are a couple of questions in the chat as well.
Yeah. Mahima had something to say.
Okay. You're asking, is the gas mass distribution uniform? No, it is not actually uniform. It will in general have some complicated distribution. What we do know, in fact, we know it's not uniform, right? Because the center of the galaxy, there's a lot more gas than there is elsewhere. So there's generally a spatial profile for it. But even though it's not, completely uniform, it is in fact the case that if you're thinking about things like the bullet cluster, when these things are merging, no matter what the distribution is, the ability for gas to scatter with other gas is extremely high. So as long as there is some density, which is like almost an average density that we can infer, it is still the case that the gas will hit other gas and get hot. So it's a very good question, but yeah, the uniformity is not really that key in trying to understand what's going on.
Distribution of mass in the dark matter, is it uniform?
No, we don't. Well, we don't know that. People often simulate it, and the simulations suggest that the distribution of dark matter distribution itself is not uniform as far as the simulations are concerned. But there are lots of people who disagree with what the simulations actually would say, because these are just computer simulations without any actual observational basis just yet. Someone wanted to know, where is dark energy in the story? Dark energy has not appeared in the story so far, and I'm not actually going to talk about dark energy in this talk because that will take us far afield. Dark energy really has to do much more with the expansion of the universe itself, more so than how it affects properties in the galaxy. But that's a separate story, and I don't want to talk about it simply because it'll take us off topic quite a bit.
There seem to be three scales. One is a solar system scale. Yes. Another is a galaxy, which is fairly wide scales. And the last one is something like the scale of the universe itself.
Yes.
So these three things are controlled by different objects, let us say matter.
Yeah. Yeah, that's roughly right. So the expansion of the cosmos itself is largely driven by dark energy, while the dark matter is something that, it plays an important role in the very early universe. But today in the galaxy, its effects are much more prominent than the effects of dark energy. All right, so there are three more questions. So let's see. So how long does light from bullet cluster take to reach us to make conclusions? Well, I don't actually remember precisely how far away it is, but in fact, we've seen it. So in a sense, the fact that we've seen it tells you it doesn't matter when it happened. The light got to us. You are correct that we are not actually seeing the merger right now. It probably happened thousands of years ago, or maybe millions of years ago. I don't know. I don't remember exactly how far away it is. But that's the good thing about the universe, is that as that merger happened, when we see the light, we know what happened, even though it happened in the past. So someone could not understand the concept of modified gravity in the Bullard cluster. So what we are trying to distinguish really is our two possibilities, right? So think about it the following way. So let us say you had observed the planet Saturn, okay, in the 1800s, and you knew that Saturn was not moving the way Newton predicted. So you're seeing with your eyes that Saturn is not doing what Newton says it should do. So there are two possibilities there. One is either Newton is wrong, the law of gravity is wrong, or second, it is the case that there is another object that is exerting gravity on Saturn that you have not accounted for just yet. So those are the two possibilities, right? So, so that is the solar system. In the case of dark matter in the galaxy, we're saying something very similar. We're saying, look, these stars are not doing what they're supposed to be doing. So there are two possibilities. Either Newton is wrong, or there are, let's call it Uranus or dark matter out there, which is extra matter that you've not accounted for. So we are trying to distinguish these two possibilities. And what's happening in the Bullard cluster is that the Bullard cluster is a system where the matter is nicely separated in space from the dark matter, because we start with the system. So usually in a galaxy, the dark matter and the matter are all mixed together. They're all one object. So you can't distinguish matter from dark matter because they're in the same position. What's happening in the Bullard cluster is that these two guys merge, and due to the dynamics of the merger, due to what's actually happening, the gas is spatially separated from the dark matter. Okay, so they're not together anymore. They're in different spatial locations. So because they're in different spatial locations, one can now ask the question, if it is due to modified gravity, we would expect all the effects to be at the location of the gas, because the gas is most of the mass in the system. But if the effect is due to dark matter, we would expect the effects, the gravitational effects, to be at the location of the dark matter, which is spatially different from where the gas is. And observationally, what we see is that the effects are at the location of the dark matter as opposed to the visible gas out there. All right. There's a great question by Inzamam al-Haq about what if dark matter is interacting with itself or the visible gas during the merging. You're absolutely right. So we were lucky that this did not happen. So you are absolutely correct that if the dark matter interacted with itself or with the visible gas, the dark matter and the visible gas would be the same location. And we would not be able to perform this experiment and learn whether it is dark matter or modified gravity. So the fact that the dark matter did not interact with itself, right, is a bound, is an observational bound on its own properties. So we actually do this. The fact that the dark matter went through itself is telling you something about the dark matter itself. Yes. Okay, so this does not have to be the case. It's certainly possible the dark matter could have talked to itself, or the dark matter could have interacted with the gas. And if that had happened, we would not be able to make this argument. Okay. Yeah, so Abhijit wants to know, what are the dark matters like a neutrino? Yeah, in fact, we think that's what it is. It probably just passes through us. We just don't know. So the next part of the talk will basically be about trying to answer these questions. Given that the dark matter exists, how do we actually see it? Okay. So I will just answer the next two questions in the chat, and then we will move to the next part of the discussion, and we can continue the discussion afterwards. So the question would be, is there anything apart from dark matter which influences your observations? Not really, because in a sense that, we can see what's actually going on. So we see the stars, we see the gas, and to some extent, whatever else we cannot see, we call it dark matter, right? So the dark matter could be a very complicated set of things. So we've just done a very simple separation. We're saying everything I can see is gas, everything I don't see, I'm calling that dark matter. And now I just want to infer its properties. Okay. Yes, antimatter also has the same gravitational effects. because the force of gravity is uniform. So someone wanted to know if antimatter also have gravitational effects. You're absolutely right. Antimatter will also have gravitational effects because gravity is universal. All right. So with that, let me jump to the next part of my discussion. In fact, I actually make Mr. Inzamam's point here, which is that we were in fact only able to discover these properties about dark matter because the dark matter did not interact with itself. Right? That's the reason why the bullet cluster story worked. It didn't have to be the case, but it does happen to be the case. So the next part of the talk, we have come to the conclusion that, look, there is a new particle in the universe, and I don't know what this new particle actually is, right? So I've only observed it so far to the force of gravity. And now that I know there's a new particle, as a particle physicist, which is what I am, I want to know more questions. I want to know, what is its mass? Okay, how heavy is it? Does it have interactions other than gravity? So like protons and electrons, the particles that you and I are made out of, they have electromagnetic interactions. They emit light. That's how we see them. Does the dark matter have other interactions other than gravity? Right? Other things it does. Why does it exist? Where does it come from? Who ordered it? So I want to know all these questions. All I now know is it's a new particle. So why is it there? Why is it doing all these things? So the challenge is basically that we need to detect these. If there are other non-gravitational interactions, we could try to detect these other non-gravitational interactions. And by detecting that in the laboratory, we can identify the properties of the dark matter. And that's easier said than done, because the reason why we call this particle dark matter is because its effects are extremely weak, right? That's why we can't see it that easily. So fundamentally, I require a technique with extremely high precision, okay, extraordinary sensitivity to see these very, very small effects. So this is kind of where I will briefly allude to my own work in the area. And I'll first start off by making some statements about technology. So this is not, the technology is not my work. I didn't create the technology. I'm a consumer of this technology. So it turns out that in the last 20 years or so, there have been very remarkable technological developments that have actually happened in fundamental physics, in the ability to measure objects. So we're able to measure very, very small magnetic fields, okay? 10 to the minus 16 Tesla. Now, for physicists or people who have used, who've done physics, they know what a Tesla is. But for other people who have not used things like a Tesla, I will tell you how small this magnetic field is. So if you think about it, there are tiny currents in our brains, okay? Our brain is some electromagnetic machine, right? It's moving stuff around. So the brain, turns out, creates very, very small magnetic fields. So the magnetic fields created by our brain are about 1,000 times bigger than these, than the small magnetic field. So a brain magnetic field would be something like 10 to the minus 13 or 10 to the minus 14 Tesla. Okay, that's a factor of 1,000 or so larger than the magnetic fields we are now able to measure in the laboratory with these very fancy devices. Secondly, we're also able to measure very small accelerations. So when I drop an apple, the apple falls down with an acceleration of something like 10 meter per second squared. This is some, how quickly an apple falls on when I drop it. Today, with these accelerometers that people are able to measure, we can measure 10 to the minus 13. Okay, so of g being accelerated due to gravity. So 13 orders of magnitude smaller accelerations than me dropping an apple. Okay, so these are technological things we as human beings are able to do today. And this is a very impressive field that has actually happened in the last 20 years or so. And I have largely worked on the idea that, look, these guys can measure these very, very small numbers. Okay, how can we use their ability to measure these very, very small numbers to detect properties of dark matter? Because dark matter requires me to measure very weak effects. And look, it's possible for us to measure these very weak effects today.
Hello.
All right. Someone is talking. All right, they muted themselves. So the question now becomes something, before we even go into my own work or something, let us ask this question, right? What do we observationally know about the mass of dark matter? So I know there is this dark matter out there. I know how much total mass there is in the dark matter. And I know the dark matter is a new particle. But what do I know about the mass of the particle itself? Like the mass of the proton, we know it is 10 to the minus 24 grams or whatever. What do we know about the mass of dark matter observationally? So what have the physicists come up with? So one thing we can ask is, what happens if the mass of the dark matter is too big, too large, too heavy? If that is the case, there's a limit that says that the mass of the dark matter should be less than 10 to the 24 grams. Okay, that is the upper limit on the mass of the dark matter. And that comes about basically because we look at the fact that I can see stars from far away. And when I see stars from far away, if there is an enormous amount of dark matter lump between me and the star, the light from the star would bend. This is its gravitational lensing that we talked about earlier. And we have not seen such bending before. Okay, so the fact that we have not been able to see such bending before puts a limit, saying that the mass of the dark matter particle, not the total amount of dark matter, the mass of the dark matter particle has to be less than 10 to the 24 grams. So that's what happens if dark matter gets too heavy. It will bend too much light in the galaxy. The next question is, what happens if the mass of dark matter is too small? Okay, so here you kind of have to know a little bit of quantum mechanics, or at least you must have learned some of these things. You have to, or heard of the idea of something called a wave particle duality. Okay, roughly the idea is that every particle in the world can be thought of as a wave. Okay, this is one of these quantum mechanical things. So if a particle has a given mass, you don't think of it just as a particle, it also has a wave. It has a certain size associated with it. And what we know is that the dark matter fits inside the galaxy. The fact that the dark matter fits inside the galaxy and the galaxy has a certain size implies that the wavelength, okay, of this particular dark matter has to be smaller than the size of the galaxy. Because if the wavelength was too large compared to the size of the galaxy, the wave would not fit inside the galaxy. Okay, it gets too fluffy. You can think of it that way. The lighter the particle, the fluffier it is. So that puts a lower limit on the mass of the dark matter, which says that since the galaxy is so huge, turns out the dark matter can be very light and very fluffy, it would still fit in, until the mass gets so small, the dark matter gets so fluffy, it can't fit inside. So that puts a limit on the mass of greater than 10 to the minus 55 grams. Okay, so this is what the theoretical physicists of the world have come up with, is that if you look at what do we observationally know about the mass of dark matter, we know the mass of dark matter is to be less than 10 to the 24 grams, and we know it has to be larger than 10 to the minus 55 grams, right? So this is not a very constraining limit. There's something like 80 orders of magnitude in mass that the dark matter could be between these two observational facts. So a lot of my work has been in trying to understand how can we sensibly probe this very, very large part of parameter space. So in my opinion, I don't really care about the lot of theory models people write down. I'm just asking the question, given that there's an enormous range of mass, 10 to the minus 55 grams to 10 to the 24 grams where it could exist, how can we probe this dark matter observationally in the laboratory? Okay, so what can we use? What is the physical facts we can use to make progress in this field? And here are the physical facts. What we know is that the total energy density, the total amount of dark matter, we know that. That is what we have measured, right? No matter what the mass of each individual dark matter particles, we have measured the total mass in the system through gravitational lensing, things like that, or the velocities of stars. So we use a very simple fact that the energy density, the total energy in the dark matter, is equal to the mass of individual dark matter particles times the number density of particles. Since this quantity is fixed, if I change the mass, the number density will change. Specifically, the heavier the mass of the dark matter, the smaller the number density, because the product is the same. What that implies is that if the dark matter is very light, has a very, very low mass, it must have an enormous number density. While if the dark matter is extremely heavy, it will have a very, very low number density. So there are numerous light particles and very rare heavy particles, because the product of mass times number is a constant, is measured. Not as a constant, is measured, is the same. So we're going to ask this question. How do we think about detecting these particles, right? What's a systematic way of detecting very light particles, very rare particles? So here is how every dark matter experiment works, okay? What we do is we build a shield, okay? And inside the shield, there's a very, very fancy detector, an extremely complicated piece of technology, if you think of it that way. What does the shield do? So we just build a detector, right? We take a shield, and inside the shield, we put a very fancy detector. And we just sit on the ground, okay, on the Earth. And what's going to happen is that we're going to assume that there is both normal matter, the matter that you and I are made out of, as well as dark matter. They're all around us. So normal matter and dark matter, they're all going through you all the time through this detector, okay? It's all around. If you build a good shield, the good shield will block the normal matter. So an example of a good shield would be, let's say, if I am interested in blocking, I don't know, radio waves, right? I'll just go inside a room with a lot of metal around it, inside a conductor, so that the radio wave does not get in because the conductor blocks it, okay? Or I can go inside a lot of rock, which will also block normal particles. Dark matter, we know, does not interact very much with normal matter. So the shield will not do anything to the dark matter at all. So the dark matter will be able to pierce through the shield and go inside the fancy detector, right? So by building a fancy detector, by putting a shield, we block the normal matter, and the dark matter, on the other hand, will go inside the shield, and it will excite. It will try to interact with this fancy detector that you have in here. The dark matter goes through the shield. That's the main idea. Now, most of the time, this fancy detector, whatever it is, you can think of it as having some dial, right? So it doesn't see anything, right? The dark matter is very hard to find. So most of the time, it's just saying, no, I haven't seen anything. And what everyone who works in this field is hoping for is that one day, if you build the right detector for the right dark matter, the dial, but the detector says, no, I'm not seeing anything, switches to seeing something, right? And if you see it, it would truly be remarkable, because you've now detected a new particle, a new law of nature. So it will be a huge consequence in terms of scientifically becoming extremely important. This, of course, hasn't happened yet. We're all hoping to build detectors which will get us to this answer. The reason why this is so difficult is because there is no such thing as one universal fancy detector. I can't just build one detector and hope to see all the possible dark matter particles, right? Simply because the range of dark matter particles can span this 80 orders of magnitude. So it's very difficult for me to build one detector and solve the problem in a simple way. You have to build multiple detectors, multiple challenges to overcome, to go and see these particles. So what can we leverage? What can we actually use to do this thing? All right. So here are the main things we can look at. When the particles have extremely small mass, let's say from 10 to the minus 55 grams to 10 to the minus 31 grams, this will turn out to be the area of interest to me today. Okay. When the particles are extremely light, there's a very, very large number of them. This is what we talked about, right? There's a huge number density of these particles because their individual mass is so small. So you can think about this as a dark wind. Okay, it's a huge number of particles blowing through the galaxy. They could also be somewhat heavy, not too heavy, okay, moderately heavy. So these don't then have too much of a number density, okay, but they're reasonable. They're not that rare. Lots of them are going through you, but they're also pretty heavy. So you can think of them as like dark atoms, right? So we're going from dark wind to dark atoms as the mass gets larger and larger and larger. And finally, it could be the dark matter is extremely heavy, at which point you think about them as objects with a very, very low number density, extremely rare, but they are like gigantic rocks, okay? Not real rocks, not rocks made out of matter that of you and I, but like the new kind of rock, dark rock that's out there. So since we don't know anything about the sector, all of these are possible. The dark matter could be these, something like a dark wind, or it could be like a dark atom, or it could be this very, very rare dark asteroid. We just don't know. What can we exploit in each of these cases to see it? So let me talk about the possibility of these dark atoms. This is what most of the community has been doing for a long time. And there are many theoretical motivations. I'm not going to go through them. People like these particles. Pardon? Okay. So suppose the dark matter is something like a dark atom, okay? Something heavy, but there's a lot of it going through. What we would actually do, what people in fact do, is that they look for the very rare collision of this dark atom with our matter. So what is literally done is that you take some detector that has got a large number of particles like regular matter, and the dark atom comes and hits this detector. As it hits this detector, it is going to make some sound. It is going to make some light. Okay, so you can think about it in this funny picture that I've drawn here. Here is some dark atom coming through, and it hits one of our atoms in a very nice detector. As it does so, it'll shatter something. It'll make some noise. It'll create some sound. It'll create some light. Of course, these are vastly amplified in this picture. Typically, these are extremely hard things to see, but that's the idea. The dark atom comes and hits our atoms, and when it hits it, it makes a tiny amount of sound, a tiny amount of light, and we collect that using our very, very fancy detectors. So people have been looking at these for the last 30 years or so, and they haven't found anything. So for me, that is motivation saying, look, guys, there is like 80 orders of magnitude in parameter space. You have looked for just one kind of particle here. Let's look elsewhere. What else can we actually do? So that's kind of, let me briefly tell you about my work, and then I will end, and then the talk will be over. So let's talk about detecting very, very light dark matter. So I'm mostly interested in this range, 10 to the minus 55 grams to 10 to the minus 39, something of that sort. Something like, 16 or 17 orders of magnitude in parameter space. Again, there are a lot of people who write theories about this. I'll ignore all of that. The main point is that these particles have an incredibly low mass, right? 10 to the minus 55 grams. And because the mass is so small, you can't use the ideas that people have been using to find these dark atoms, because the dark atoms are relatively heavy. So each atom has quite a lot of mass, quite a lot of kinetic energy. So when it comes and smacks into you, it has quite a bit of energy it can give out. But these guys in the very low mass region have such a small mass that each individual particle has a very small amount of energy. So if I try to detect this very small amount of energy, it's completely hopeless. I can't actually see that tiny amount of energy. But what we can make use of is that when I think about this very, very light dark matter, I think about it as a wind, right? Like there's such a huge number of particles that this should be considered as a dark wind blowing through the galaxy. So how do you really detect wind? You don't try to detect wind by measuring the collision of each individual wind molecule, right? That's such a small effect. What you want to look for is that all of this wind can collectively do something. So when I try to detect wind, I do that through a windmill. In a windmill, what's actually happening is that all of the wind molecules are jointly rotating some fan, some blade in the windmill, right? So we're looking for the collective effect. All of these wind molecules come together and they jointly rotate the vanes of a windmill. That's how you detect wind, okay? So we're similarly going to look for the collective effects of the dark wind blowing on materials. So let me give you 3 kinds of ideas. So one idea that we've proposed is that the dark matter, which is just this dark wind, as it goes through spins of nuclei and electrons, so that's what's shown over here. There's a dark matter, there's a dark wind, it's blowing through this nucleus or electron. It will cause the spin of that electron or the nucleus to rotate. So I have my dark matter coming through, I have a bunch of nuclei, the dark matter goes through, the spin of the system will rotate. The spin of nuclei, turns out they carry a magnetic field. Okay, so what's happening is that as the dark matter blows through, the spin rotates. As the spin rotates, a tiny magnetic field is created by that rotation, and you can measure that tiny magnetic field with this very, very fancy magnetic field detectors that people have today. So that is one experiment that we have proposed, and it is now in construction at Boston University and Mines. Okay, so here's the basic idea. We take a sample of material. We have all these spins. Okay, so that's the arrows that are shown over here. These spins are aligned in one direction, and then the dark matter comes and does its thing. The dark matter comes in. If the dark matter exists, it will cause the spins to rotate a little bit. As the spins rotate, the magnetic field of the system, it used to be in one direction before, in the original direction. Now it's rotated a little bit. And that small change we can measure with this very nice magnetic, with this magnetometer or a squid, which is measuring a small amount of magnetic field. So that is basically one experiment that we have proposed, and that is in construction. And, you know, I won't go through these plots, but the idea is that it actually has interesting scientific potential in discovering new particles. The other experiment I proposed is called dark matter radio. And the idea is something very simple. Let me take a shield, and inside the shield, I'm going to create a very fancy radio. So the dark matter comes in, and what it does is that inside the shield, so here's what I'm literally going to do. I'm going to take a shield. Inside the shield, I'm going to stick a very, very complicated radio. Okay, so a radio is something called an LC oscillator. That's the fancy word for it, but that's just what it is. It's just your radio set. Okay, so what's happening is that the dark matter comes in, and it creates a current in this radio. So that's another effect that the dark matter can do. The dark matter can come in, it can create small currents in this LC oscillator or in this radio. And what's happening is that when you create the small current in this radio, okay, that small current will also create a small magnetic field. Okay, and that small magnetic field you can basically measure with this very precise magnetometer, like the squid. So that's fundamentally the ideas. We're looking at the fact that the dark matter comes in, it can cause a spin to rotate. As the spin rotates, it changes the magnetic field, which you can measure with a magnetometer. Or the dark matter comes in, it creates a small current, and that small current creates a small magnetic field, which also you can measure with a magnetometer. And the final thing we're going to talk about is that the dark matter can come in and it can exert a small force on atoms. That's another thing the dark matter can do. And if I exert a small force on atoms, I can use these very, very precise accelerometers that I talked about as a way to measure these small forces on atoms. So let me show you what the experiment is. The experiment basically involves people taking two different atomic clouds. Okay, people take rubidium-85, which is one kind of isotope of rubidium, and rubidium-87, which is another kind of isotope of rubidium. And basically, they're going to drop rubidium-85 and rubidium-87. And we're going to see if one of them falls faster than the other. So what's happening is that the dark matter exerts a somewhat different force, a somewhat different acceleration on rubidium-85 versus rubidium-87. And we're going to drop these two guys. Under the force of gravity, both of them are supposed to fall at exactly the same rate. So Galileo famously did this in the Leaning Tower of Pisa. He dropped two objects and noticed that under the force of gravity, both of them fall at exactly the same rate. We're going to do that same experiment, but with extraordinary more precision, where we're going to now drop rubidium-85 and 87, and under gravity, they'll both fall at exactly the same rate. But if there's a new force, for example, a force due to dark matter that pushes on 87 differently than 85, they'll fall somewhat differently. So that is the other experiment that's actually going to happen as well. It's also now funded, and it is being constructed at Fermilab in the United States. So with that, let me actually conclude my talk, right? What I've been motivated by a lot in the last decade or so is that look at the large span of possible dark matter masses. It's 80 orders of magnitude in range. One should not look at this big problem and say, I like one theory and I'm going to go and look at that theory and see how to, predict how to detect just that dark matter. I take the attitude that, look, there's a huge range of parameter space. What is a systematic way in which we can cover a large range of masses? And that's what I've been up to for the last decade or so. So with that, let me conclude my talk. I'm happy to stick around and answer more questions. But thank you very much for this opportunity.
It's a very brilliant talk. Surjeet, I'm very happy to hear. It's actually very well. You explained it in simple language to the extent of this thing. I think there are several questions which have come. Vijay,
Yes.
Probably you can post those questions from the chat.
There are already several
One
on chat.
question is dark matter, does it not interact with itself through gravity?
Yes, the dark matter does interact with itself with gravity. In fact, we do see that. In the early universe, we have conclusive evidence for how dark matter interacts through itself with gravity. You're absolutely correct, because gravity is universal. We certainly see that. So the question we're asking is basically, are there non-gravitational interactions? So that is what the pursuit is, because gravity indeed is universal. We certainly see it.
That is expected to be much weaker than the interaction with itself, self-interaction with itself.
Yes, yes. And then someone asked, can dark matter be many particles like matter? Yeah, absolutely. We just don't know. We have no idea. So dark matter, it's certainly not the case that we know that all the dark matter has to be one kind of particle. It could be many different kinds of particles. So this is indeed one of the reasons why we want to do these experiments, is that by detecting, let's say, this dark matter in the laboratory, you might actually be able to learn how many kinds of particles there are. And we would also expect it has its own antimatter, all that kind of stuff. So indeed, in many ways, we would think it's just like a regular particle with just extra properties that we don't actually know about. All right. And the other question was, is there any evidence dark matter follows same physical structure, hierarchy, or laws as matter? For example, wave-particle duality may not hold. Good. So you are correct that we are assuming that the dark matter follows the standard rules of quantum mechanics, which was one of the arguments that I made. So at this point, that is just a hypothesis on our side. I would say it's a very reasonable assumption that the dark matter obeys those properties, because it is the most conservative assumption one can make, right? Because we know the dark matter is out there. We know it's a new particle. So in principle, perhaps it is able to do something beyond the regular particles that we know about. But in general, right, like if you think the dark matter is doing something so strange, maybe it doesn't obey quantum mechanics, things like that, you might very reasonably expect to see those kinds of effects also in regular matter. So somehow the most conservative assumption is that the dark matter obeys the ground rules, but it just has new interactions. But yeah, I mean, in principle, it's possible that it's something totally wild, which would be very exciting, which is why one of the things you might want to detect it. But it is not unreasonable anyway to assume that it obeys the standard rules of quantum mechanics.
There's a question. Go ahead.
Someone, yeah, I mean, I can just read the chat out. How did we conclude that dark matter is only inside a galaxy and not outside? Well, we did not conclude that. In fact, we would expect dark matter is both inside the galaxy and outside of it. What we definitely know is that there's a lot of dark matter in the galaxy, right? Because that's how we are seeing its effects in the first place. We are seeing its effects by how it affects stars and stuff like that. So we know there's a lot of dark matter in the galaxy. And it is just that observation that we're making use of in constraining its actual properties. Someone asked, could dark matter be a wave? Absolutely. In fact, all particles are waves, and so there isn't really a fundamental distinction between a wave and a particle. So dark matter could absolutely just be a wave. In fact, all of the light dark matter that I talked about is best understood as a wave as opposed to a particle. Great question. If dark matter is everywhere, how do we determine the rate of spin change? That's a wonderful question. So what is true is that the dark matter is this light. It is a wave, right? That's the correct way of thinking about it. So at least during its period, okay, which could be pretty long, it turns out. So for the particles that I'm looking at, the wavelength of the dark matter, or really its periods can be, megahertz, kilohertz, or even a period as long as a year. So with that wave comes a period. And we are basically looking at the rate of spin change during that period. Of course, we don't know the exact mass, so the period is something we need to keep changing and keep looking for. But that is absolutely correct. We will be looking for the spin change during a period of the gravity of the dark matter. Someone asked, is dark matter composed of the same quarks that makes visible matter? So that is something we know. It is not made of the same quarks that we are made out of, because in a sense, if that is the case, it would have interacted with itself more strongly than what we are seeing, right? So we actually know for a fact that the dark matter is something that does not interact much with regular matter. So that's why we know it's not made out of the standard kind of quarks that we are made out of. There are some people in the community who like to think otherwise, but I think they're wrong. They have to work very, very hard to come up with models that would evade all constraints, et cetera, and even then they don't really quite make it. So I think we know for a fact that it's actually not something made of regular quarks. How can we determine the presence of dark matter if it does not, if it does not exert pressure on normal objects? Maybe you missed a word there. Yeah, so actually we are trying to, what we're hoping to see is the incredibly small pressure that it exerts on normal objects. So that's why it's so hard, right? We know it doesn't exert regular pressure. So we're trying to detect the extremely small pressure that we hope it does exert on regular matter. So that's why we do it. About rubidium, how do you distinguish the effect of dark matter from modified gravity versus fifth force? Great question. So again, this goes back to the period that we're talking about. If the dark matter is actually a new wave, which is what this will be, it will acceleration that it actually exerts will be time varying. It will be varying at a frequency equal to the dark matter mass, and so a new fifth force or modified gravity has no period associated with it. While the dark matter wave will move back and forth. So as it moves back and forth, the force that it exerts on rubidium will be changing at that frequency. So that's basically how we distinguish it, not just from the effect of modified gravity or a fifth force, but even from standard backgrounds, from Newtonian backgrounds that exist in this case. Bhaskar asked this question, can this be in any way used in technology? The answer to that question is, I don't know. We don't know even what the dark matter is. So certainly if the dark matter is, it's possible the dark matter is something called a primordial black hole, something like that, right? So if that's what it is, it can have technological uses that nobody's thought about. If the dark matter is a very, very light particle, I don't know. Since we don't know, it's very, very hard to answer that question. But I'm not particularly motivated by any technological applications of this kinds of particles. So like this is the kind of question that happens all the time when you go up to get funding. So the answer always is the following. First of all, we don't know. So depending upon whatever it is, maybe it has technological applications or not. I'm driven by just my curiosity. But what is true is that the technologies that we use to detect the dark matter. So when I'm trying to come up with a technique to detect dark matter, I'm creating an incredibly powerful magnetometer or an incredibly powerful accelerometer. These technologies by themselves have enormous technological implications because with a very powerful magnetometer, I can measure the brain. And that can be used to understand actual biological facts about the brain. Perhaps people even use this these days as magnetic imaging to look at cancers and things like that, right? So the technologies of physics are more broadly useful than just physics itself. All right, if so, the dark matter doesn't interact with the shield, which is made of normal matter. How does it interact with the detector? Very good. That's a great question. So yes, the dark matter interacts extremely feebly, both with the shield and the regular matter, which is why I need all these very, very fancy detectors to detect it inside, right? So I have to, so the job of the shield is that it blocks the vast majority of the standard model or of the regular matter, while the dark matter goes through. It very rarely interacts with the your detector, which is why your detector has to be so precise to be able to see this very, very small effect. All right. Is there any imbalance in the matter and energy supposed to have produced in Big Bang? Is there any other indication for the presence of dark material in theoretical physics? Let's see. Yeah. Is there any imbalance in the matter and energy? Well, I mean, we would broadly just say that, you know, as far as physics is concerned, matter and energy are the same. They're like sort of one and the same, right? So you can really go between the two. So it is true that in the Big Bang, for example, we think a lot more radiation, a lot more energy than regular matter. But to some extent, you know, they flow between each other. So I wouldn't really separate them as matter and energy being different. Is there any other indication the presence of dark energy in theoretical physics? Yes, I mean, I wouldn't say it's not really in theory, but more in observation. So we have seen many other reasons why dark matter has to exist. So for example, if you look at the very early universe, properties of the very early universe also require, independently of everything that I've said today, independently require the existence of dark matter. So that's a separate story, but we do have other indications for why there is dark matter there. What if we've been using a strong shield to avoid matter as alpha particles can be stopped with a paper? Can we use a light shield, but it's very difficult to construct one? Well, I mean, you know, broadly, the purpose of the shield is to block regular matter. So the dark matter, you know, in general, will just go through the shield. So the shield's job is to just block regular matter. So as long as the regular matter is blocked, it's perfectly okay. Because the dark matter is just going to go through. So that, you know, the shield itself, the job of the shield is so much to block the regular matter more than the other kinds of things. All right. While merger takes place, whether bullet cluster's volume gets affected. Yeah, the merger is a very complicated thing. So all kinds of things happen. So, you know, the cluster itself is totally disrupted. So it's not like there's any reason why the initial volume has to be preserved. As the merger happens, the cluster is totally messed up. It gets all over the place. Okay, someone has a question about black holes. This doubt is related to black holes and gravity. Black holes are mostly depicted with light all around it. Why is that? Taking that a black hole is a three-dimensional object, it must observe light from it. So when people often talk about black holes, what they're actually looking at is the fact that around the black hole, there is something called an accretion disk, which is essentially the matter around the black hole that is colliding with the other gas around it and getting very hot. So when people talk about black holes, usually what they're saying is that there's a hole in the middle and there is this gas around it. And it is that gas that we're actually seeing, right? So in some sense, it's a lot like dark matter because we can't see directly what is dark. We can only see what is the effect of the dark object around on the particles around it. And when we see black holes, we're literally seeing the gas around the black hole. That's what we're actually seeing. All right, so more on rubidium. Since the mass is unknown, it can be such that the frequency is so small that it will not be distinguished from modified gravity. Yes, you are absolutely right that if the frequency is very, very low, let's say a year or something like this, then basically I'll find it harder and harder to distinguish it from you know, regular dark matter. But it's an interesting fact that at the end of the day, the lowest frequency dark matter there could be, which is 10 to the minus 55 grams, corresponds to a time scale of 1 year. Okay, so if you, let's say I detected this dark matter, I can then do this experiment where I wait for 2 years, 3 years. Okay, so if it's really dark matter versus modified gravity, then every year the frequency will change. The oscillations will change, and I can see that. So in principle, it is distinguishable, but of course, it's in practice that gets harder and harder. But in principle, it's anyway possible. Can dark matter also be swallowed by black holes? Absolutely. Dark matter interacts gravitationally, and gravity will cause black holes to absorb dark matter as well. So I think that's pretty much all the questions people have asked.
Can I ask you two questions?
Yes. Yes, yes.
One is this 10 power minus 55 grams.
Yes.
In terms of electron volt, it will be some 10 power minus 26 or 25?
It's more like 10 to the minus 22 EV.
So that is a kind of a limit for the dark matter?
Yes, yes.
as 10 power minus 22. It cannot be greater than that.
Lower than, it can't be lower than that.
Using that.
Yes.
Okay, lower than that. Okay.
Yeah, it can't be lower than that. Exactly.
Okay. Now, the conventional wisdom is in the evolution of the universe, the galaxy formation, where the dark matter plays a role.
Yes.
It should not expand too fast. The dark matter should not escape in order to allow the thing. So that itself will put a limit on the mass of the dark matter candidates, right?
It does. So the limit ultimately comes down to the fact that we have seen these dwarf galaxies, right? So we know the dwarf galaxies exist, and you're correct that if the mass gets very light, the dwarf galaxies themselves will not actually be able to form because they get so fluffy. So there's something called a pressure that comes from this because the particles are so fluffy. So it's indeed the existence of dwarf galaxies that actually puts this limit of 10 to the minus 22 EV on it.
Okay. Thank you. It's very nice. Very good talk. I think that's what everyone is saying. We are very happy.
Very good. Thank you for the opportunity.
Yeah, a couple of more questions recently come.
Yes. Possibilities of dark matter being another universe, which is somehow mingling with our with such gravitational effects. Hey, that's a great question. I've recently speculated on this. We don't know the answer to that. It would require something quite wild, like perhaps a modification of quantum mechanics, something like that. But I think it's certainly so the question that Inzamam asked was, is it possible that dark matter somehow is another universe, which is somehow mingling with ours with such gravitational effects? Most people would say no, and I would have probably said no as well until 8 months ago when I began playing with perhaps modifying quantum mechanics itself, and there maybe such things are possible. So I wouldn't dismiss it immediately as I might have maybe a year ago. So it's certainly possible. Now there's another question, which is why does dark matter affect objects that are further in galaxies than center of galaxy? Well, in fact, it affects all objects. It just has to do with the fact that there is a lot of mass in the galaxy, and so the dark matter affects everything. So it's not like it affects one thing differently than the other. It is just the case that dark matter perhaps is more piled up in the center of the galaxy, so its gravitational effects are more visible nearby than further away.
Right. So,
okay, Rajan.
Yeah, we are at the end of the event. I ask, I'll request Pugadarasu to give vote of thanks.
Thank you.
Pugadarasu.
Yes. Very good evening to everyone here. First of all, I would like to thank the speaker today, Professor Surjeet, for this very, very insightful lecture, for walking us through the fundamentals and detailing the modern picture, and for also outlining your very recent approaches on tackling this problem. And we dearly hope to succeed. And I would like to thank the PSL organizers, Vijayan sir and Sundar sir, for bringing this meeting together. I'd like to thank Professors Ramanujan and Professor PRG for summarizing the work of TNSF and for introducing the speaker today. And I'd like to thank the audience today for having gathered here on this wonderful evening. Thank you, everyone. Have a good day ahead.
Thank you.
Thank you very much. Bye.
Thank you very much. Thank you. Bye.
Thank you. It was brilliant.